See, I was seeing if you were paying attention. So, and then the other would be products of sums, right? Fair enough? So, within this, you would have two, I did this earlier. These are adding and these are multiplying, right? So then you would add A and B and then multiply it with this C and D added together. So in that sense, you would have one level of, remind me again, AND gates, OR gates, and OR. Okay. Sorry, it's been so long since I've done these. So you'd have one level of OR gates and then one level of AND gates that this goes into. Does that make sense? Now, in retrospect, you could also do...
But the overall circuit is a two-level circuit.
Right. Something like this would be a two-level.
But
yeah.
How do you figure out the number of waves and determine the level of circuit?
No, not necessarily. Because what if I have A plus B plus E and that times C plus D? That would still be a two-level, right? But this guy would be 3 inputs. Does that make sense? So it's not necessarily that easy, per se. There's some problems that actually make it where you have to have multiple levels, depending on what you're doing. So if I was looking at one earlier that basically it was using NOR and NAND gates, and those make it a little bit more complicated, because if I say that I wanted to put all of this right here through a NOR gate at the end, then you would have an extra step that you would have to go through. So you could have another level. Does that make sense? And so it's really a matter of sitting here and evaluating almost from the inside to the outside. So it depends on how you do it, because you could distribute this and make it still 2, right? Or you could have 3 levels like you would have before with the 3 here, which is plusing, and you could have the 2 from here all going into an AND gate, and then you could also have that going into AND gate. I mean a NOT gate. Or you can make this guy right here a NOR gate and get rid of both of these levels.
Yeah.
Does that make sense?
You see on the very left side, you have an OR gate and an OR gate account.
These two?
No, right. On the one that right there. You have like an OR gate and an OR gate.
Mm-hmm.
So that's one level.
Right.
You have an OR gate
and the AND gate
on the same vertical axis and still have
I mean,
OR gate.
I don't think so, because what you'd have is the same kind of, you would start with these on the inner side, and those would be one level. Does that make sense? And then the next level would be the next step out of the parentheses. And so it would then trigger a next level.
So it does not have to be OR and OR. It could be OR and AND.
Right, you're basically asking is it often that you see something like this?
Yeah.
And what I'm saying is, what would you have here? You'd have 2 variables, say A and B, and say you have 2 others, C and D. Does that make sense? And then so now you're kind of, bless you, kind of confusing things a little bit. Say they're going into this. So then what do we have? We have A plus B times CD, whatever, if you want to stay that way. So that's kind of something that, I don't know, have you seen something like that? I haven't, personally. This is kind of because you kind of stay with one consistency, right? So this would be your max terms, and this would be min terms. So you're mixing the two up. And it's not that you, I can't necessarily say that you can't do it, because I haven't seen all the problems in the world to know whether, but through this book, I read this whole book when I was taking the class. Didn't really see anything like that. Because what's happening is, here you're looking at the ones on a K-map, right? And here you're looking at the zeros. How would you do both at the same time? Huh? Okay, so you're saying like A, C, D plus, or times B, C, D? Right, but...
It's plus, right?
Huh?
It's plus,
Oh. Yeah, you're right. So, in that respect, you would. I could see that. But do you see that we also just did a Boolean algebra there? So, obviously, you can simplify this. You see what I mean? And so, if you're talking about your final level, which if you're doing something like this, you would want a simplified term. Because without the simplified term, you're spending more money on logic gates that are unnecessary. So you would need, once you go here, you want a simplified version. If it's not simplified and you can do some Boolean algebra on it, then you're not to the point where you're ready to actually design something like this. Does that make sense? So, you could do something like this, don't get me wrong, but is it the most simplified? Is it the most efficient? Is it, you know what I mean? That's really the questions that you got to ask yourself. Thank you for that. So, that is a good way to look at it for sure. Honestly, I would throw it in a K-map and see what happens. Me personally. But, does that kind of answer your question a little bit? Okay. Anybody else have any questions before we get started? Alright. So the problems I have are here somewhere. I've got 21 F and G that I was looking at doing. And then this 42, all from chapter 7, since the y'all would like, and show y'all that.
I have one question. On the first one, we see 7.21, number 8.
Mm-hmm.
Do we have to have all the literals to put that in the K-map, or we need to draw a table for that? Or we don't have to draw the K-map?
I would draw a truth table. Because when you go through the truth table, you can see, okay, B, not D. That is a certain number through the truth table. And that particular element is a min or a max, depending on what you're pulling. And so it's important to be able to look at those. Because you're not going to be, you can go directly to the K-map. I remember doing that. Where you basically find out, okay, I have so many variables that are there. Where would that be in a K-map? Let's go. Yeah, y'all want to try and do something like that? Alright, it's been a minute, so y'all are going to have to bear with me. So let's see here. Let me write this down. So, F, A, B, C, D equals B, D plus B, C, D plus A, B, C, A, B, C prime D plus B prime D prime. So if you're looking at this, you've got A, B, C, D, right? And so, is it 0, 0, 0, 1, 1, 1, 1, 0. No. Alright. So we're all good there, right? So if we're looking at this first term, we're looking at B D prime, right? So this would mean that B would be a 1 and D would be a 0.
Yes.
Alright, so where is B always a 1? So it's a 1 here and a 1 here, right? And then where is D always a 0?
We're on the last row.
Yeah? So that gives us what we need to look at, right? The question is how many ones are we going to have to place on this map in order to get a B plus D?
Or 4.
Okay. So then we have all 4 of these. Do you all agree? Where those arrows combine? So when this is B is a 1 and D is a 0, got this. Same here. Same here. And same here. Y'all agree with that? So that is a way that you could go straight to it. We can do another one. Alright, so B prime, or you know what, I can just write up here. So B would be a 0, C would be a 1, and D would be a 1, right? So there we would have B, a 0 here, and a 0 here. And then CD is 1, 1. Where does that happen? Multiple places or just one place?
Just one row.
Alright, so it's here. So then you write where those guys cross. Cool? So that's basically how you go about it. So you can also look at it in chunks like we did over here. We included these two all together. It kind of makes it easier to see that that's one area. So A would be 0, B would be 1, so that would give us the 0, 1 right here, right? So I'll do something different to show it. And then the C would be a 1 also. So C is a 1 here and here, right? So if we follow that across, you'd have this one and then this one. Yeah? Following? Cool. So the next one we're looking at is this last one. I'm going to write it over here so that I'm not getting a mess over there. So here's another one that we're looking at, and it will be 1101. So this we can look in groups again. So we've got this 1 1, which is this guy here, and then this 0 1, right? So this guy here. So I'm sorry?
Oh, A prime. Sorry.
Oh, I'm sorry. So this guy was a prime. So that makes 0. So instead of this guy, we would go here. It's the only difference. You scoot over 1. Okay? So you got a 1 there. Cool? And then this last one is B prime, D prime. So you're looking at B being a 0 and D being a 0 also. And just like this first one, we would have 4 1s that we would place. So B is a 0 here and here. And then D is a 0 here and here. Right? So that would give us this guy, this guy, this guy, and this guy. Yeah. Cool. So then you can go from here and actually make your circles and all that nice jazz. So if you're looking at that, anyone see where else we could circle first? Yep. So we can go like this and like this. Yeah. And then we could go these 4.
Group of 4.
Huh? Oh, you win. I didn't see that. I was seeing a group of 2. Cool. And then you can go from there and name these guys, right? Which would give us our simplified from here. Obviously, this is not simplified. What we're looking for is simplified. So this first one, we're looking at CD, and then both being 0, and then this bottom row, which C is changing from these two, but D is not. And so D would come out as a D prime. And then all of these are changing, right? So that's it right there. Because A and B are always changing here, up here. Alright, and then we've got 3 groups of 4 that we got to do. Alright, so this one here, we're looking at from AB being 0, 0 to AB being 1, 0. So B is not changing. And so it would be B prime. Get this out of the way so it doesn't. And then from here we're doing the same thing. What's changing, what's not changing. We're looking at C always being a 1. So we have it BC. Cool. And since we have two other groups of 4, and we just did a group of 4, came out with 2 variables, we know these other 2 will be 2 variables also. So this long guy here, you can take him. And what's great about this guy, which I like these a lot, because the whole column is not changing. That gives us 2 elements, and we don't have to go any further. So A, B naught is what we, A naught, B is what we pull out. And then the last one we have is this guy right here. From here we're looking at these 2 up here, where A is not changing, and it happens to be A naught that we're pulling out. And then these 2 we're looking at is CD. C is the one not changing, so we pull it out. So then we've got a simplified expression here, plus A prime B plus D prime.
So that's how chapter 7 works.
Yes, the other part of chapter 7, this is just simply like you were asking, do I have to do a T-table? This is basically just showing you how to accomplish it without doing a T-table.
From chapter 5. Looks like it was a confusion.
No, he asked a question, and that's what I did to answer it. He asked about this problem, and if he was able to go directly from this problem to a T-table. If you wanted to go beyond that, what chapter 7 does is says, okay, now give me a 2-level gate expression.
On the first row, it's C prime D.
Huh?
On the first row, it's C prime D prime.
Yeah.
Right, but it's also grouped with that group of
On the bottom.
On the bottom.
Oh, so it's a stack of 8.
Yeah, so it's a stack of 8.
It's a stack of 8. You see that? Yeah? Okay, so going on to what chapter 7 says is, we can go ahead and do this one. So it basically says a 2-level NAND gate. Well, we know that NAND looks like that. NAND gate has this. So and NAND, right? So how would we be able to do 2 levels using this symbol? So basically you're going to have to work through this right here in order to get it in a form that you can use nothing but NAND gates. What I was seeing is, I'm going to rewrite this expression here. So basically what you're looking at here is, how do I get this into 2 levels of NAND gates? And a lot of these problems were like, okay, here's an expression that's unsimplified. Here's how to simplify that, which is with K-maps. So, of course, it's chapter 5. You're building on that, right, though? So then you're using these gates. So this one particularly says 2-level NAND gate. So what you want to do is get this all into NAND. So we want a product of products. Does that make sense?
Yes.
So in order to do that, we would want to prime it twice. And when we do that, we feed these into each one of these. That goes to the plus, that goes to that component. You're distributing, right? So after that, you get A prime C, all primed, times, yep, and then C primed, and A prime B primed, and then D prime primed. And all of that primed because we only brought in one of these. We still have one left. So basically you're using your Boolean algebra as well as your K-maps, and then you're putting it in the form that it wants. It's 2-level NAND. That was close. So we've got 1, 2, 3, 4 of these guys. So technically we only have 3 because this guy can just come in wherever we want him to because he's not multiplied or by anything or and with anything, right? So here you're looking at A prime C, B prime C, A prime B. And then you could take all of that plus this guy, which doesn't need to be anything but D prime, just a wire, right? And putting it into another NAND gate to get your function.
So what do you mean by 2-level NANDs? Is like,
This is level 1,
alright,
and this is level 2. So this whole
so
area here. So every time you step up, it's another level. Will we cover more? All right, 42. So this one is basically, you're given 3 different functions, and they ask you basically to put this in an AND OR gate circuit in order to basically get all these together. Yeah.
so it's into 2-level and OR gate circuit. So
A minimum of 2 levels.
minimum.
So you can go more than that, but not less than that.
Okay.
Does that make sense? And multiple outputs, so you can have multiple things going into these, multiple, whatever helps condense it down.
Okay.
And then you've got 3 functions that you're basically trying to combine. Is that right? Okay, no, you're not trying to combine them. You're trying to get a circuit for each of them that are all connected, but it's outputting the 3 different functions. Does that make sense? So think of one function. I would have the different and or gates coming in and putting out a function, right? So they want us to basically do that for one function and then use the different wire lines, logic lines, whatever is on those particular wires to also help us create the other functions. And then at the end, we'd have these 3 functions outputted. Cool? Alright, so let me go back over. Alright, so this guy is, we've got a minimum of 2 levels. And these 3 different functions that we want to create. So this is basically taking everything that you've learned so far and putting it into a circuit that you would be able to build out in industry, whatever. So I guess let's go ahead and do that. So I've got these 3 set up, so I didn't have to draw them. Can y'all see that? I'll use this other one. One zero, yep. Should write in this. Alright, so you got also the naming convention. Yeah, it starts at 0, 1, 2, 3, 4, 5, 6, 7.
Well, no, the 7's on top of 6.
Oh, you're right. Sorry. 8, 9, 10, 11, 12, 13, 14, and 15. Cool. I'm only going to do that for 1. So, here we've got, they're all in minimums, so that's nice. Probably why I picked this. Yeah. So, so here we've got 10, 11, 12, and 15. And these guys are in 4, 8, and 14. 8 and 14. Cool. Alright, so then we've just got circling again, right? So we've got these guys and these guys, I believe. Huh?
That's it. You don't circle the don't care, right?
Yep, we don't care. If it helps us, great. If it doesn't, then yeah. So, let's see here. So then we just pull them off, right? So we know that these are 4, so let's see. We've got 1 is changing from C here, from 0 to 1, and then D is not changing, so got D not, and then over here we've got A not changing, and then in this guy here, let's see if I can make that a little bit, we've got C is not changing, and we've got A over here, it's the same. Cool. Alright, so the next one, we've got same kind of stuff going on. Just gonna go ahead and plug through this. We've got this here, this here, this here, and this here. And then don't cares is in 1, 10, and 12, which is up there. Cool. So then, what we've got? We got 2 groups of 4. You'll see them. 4.
Oh, yeah.
We got this guy, this guy, this guy. So then this guy here is going to be C prime, D prime. And this guy would be C prime and B
B prime.
prime. Yep. Alright, so one of the things that you kind of want to look at when you're doing this is there anything matching between these two? I'm not really seeing anything right off, but that's kind of one of the things that you want to do in a problem like this. Because ideally what you're going to be looking at is a multi-level system that's basically branching off of it itself. So if I've got something here, this is going to represent an AND or OR gate, right? So I've got some function that's going into a 2-level AND OR gate, whatever I have there, and putting out a function. Say this is my input, this is my output. So our hope is to have, you know, maybe input going into something here, but also grabbing something from this guy to then put out output number 2. Does that make sense? And we're basically trying to jumper over and get what we need.
I just want to make one thing clear. So the question is asking us to use the same input in these 3 functions and give us 3 different outputs. That's what the question is asking.
It's asking for us to basically integrate all these functions. So if we were to look at this as being one circuit, it wants us to integrate them where they're using components from the other circuit in order to, again, lower costs. Does that make sense? And so instead of, you know, taking this guy and having him be another input, we're using what's already in existence on our circuit.
Alright, so here, at output 1, I can say that's a 2-level. So output 2 is also 2-level because you gain from the first, you integrated from the first level.
Yep. Because you're getting whatever output's coming from here, right? And you're pulling it in. So it's already been through one logic gate. And then just because we're not using a logic gate here doesn't mean that there's not one already in the path of those inputs. And then they're going into another one, and this could be just a straight pull from one of these variables. Who knows? It just depends on what we're looking at. Alright. So that is probably the hardest part about a problem like this, is we're trying to make things resemble each other. More specifically, these different values that we got out, we want them to be similar. So you really got to kind of analyze these K-maps in order to see that. Like, what could I get if I were to circle this a different way? Maybe it won't be the most simplified for this particular function, but it will be simplified in the fact that I'm pulling something from this function. So with the don't cares, though, you have a lot of different options. So that's kind of where things kind of get sticky, is like, what could I do from, like, over here, this might be the most simplified, but is it simplified where it will help us build this guy? And so at this point, we're not looking for the most simplified of this particular function. We're looking at the most simplified for the entire function, for all of these guys. And so that's kind of where things get a little bit harder. You kind of have to look at this and say, well, if I only circled, you know, maybe these middle 2, what would happen? Would I get something that would be closer resembling this guy? I don't know. But it's something that we could look at. We'd still have B involved, right? And then we'd have C prime, D prime, and B. So that's but if you're looking at this at the same time, look at it this way. If I were to have what I'm talking about, these guys here circled instead, that would give me C prime, D prime, B, right? So the reason why I circled those 2 is because if I didn't have this guy as simplified as possible, and I see that these 2 squares are both the same squares on both functions, both K-maps. So if I circle these guys and I get this here, then I could do the same thing here. And I'm still covering this one here, right? So by doing that, I'm allowing this particular output, this particular group of variables that I'm getting out of this K-map over here to be the same over here. Does that make sense? And therefore, these two can be tangent off of each other. And so that is kind of how I view it. I don't know if it makes it easier for y'all to see it, but because these don't cares gives us a lot of options here. So I could circle these two, I could circle them with these four like I did originally, or I could circle them over here. Does it matter? No, because we're still covering this guy, right? And in this particular case, this problem wants us to connect all these. So we got to find a way to connect them. And if we see something in common like that, we could go ahead and connect them. Does that make sense? Any questions so far? All right, so I guess the next step would be seeing if we could get number 3 to do something similar to one of these two. All right, so then we've got the same kind of method here, placing our ones and then our don't cares. 13, where's it? 13, 14, and 15. And then our don't cares are in 5, 9, bless you, 12 and 9. Y'all see that? We've got the same overlap here. So we can do the same kind of thing and say this guy right here is what we want. That way we're just sharing this line all the way across.
Alright. Since we have 3 of them that almost like the same thing, alright? At the first box, the first one, since we didn't circle it at the beginning, can we just circle it now? Just because we want it? Even though it's with a don't care?
So you're saying making this change, is it going to affect anything?
No, I mean,
after the fact?
Didn't we, at first, at the beginning, before we wanted to circle that one with the X, are we allowed to do that since that's a don't care?
Right. Well, I mean, it's the same thing we did here, right?
But we grouped that with the other 2.
Right. This right here that I had originally, this was the most simplified version for this particular K-map. But what we're interested in is the most simplified version for this entire 3 K-maps. So this is having a don't care also. And so whether we use it or we don't use it, we don't care, for lack of a better term.
Okay.
And so being that we haven't built a circuit yet, we haven't gone that path yet. This is all computational. If we change this, it's not that big of a deal.
Okay, so
And
we just add.
yeah, so no, what would happen is we don't need this guy anymore. This guy's gone. And so we're using this guy and this guy now.
Alright.
Does that make sense? Maybe I didn't make that clear before.
No, it makes sense.
So we're not going to use all 3 of these terms. We're just going to use these 2.
You're going to use the 4, the 1, X1, and you're going to use the X1, that's it.
Right, I'm going to use these guys and this guy.
Yes.
Mm-hmm. Yeah. And because this guy, like I said, we don't care whether we use it or not. If it helps us, great. And if this was our only one, yes, use that and get these 2 guys, and that's your most simplified version. But being that, like you said earlier, that's chapter 5. We're working on chapter 7, trying to see how we can combine different things and make a bigger circuit with respect, thinking about the fact that we want to make a bigger circuit. And so then from there, you would basically do the same thing here. So we've got our commons. So from there, we could go, our normal K-map blocks. And we've got our common. We don't really care. I mean, like I said, if you look here, you could do the same thing. if you're not doing if you're trying to simplify it according to that particular K-map, you would have this bigger guy, which would simplify this particular circuit more. But, and the same over here. We've got this guy that we could use to make K-map 2 bigger. I mean, more simplified.
So you have to have at least one common. That's what you're saying. I just want to make sure.
Yeah, I mean, for this particular problem, it just says that we want to be able to use, like if he's one circuit, I'm another circuit, I want to use one of his inputs to help me out instead of having it run through, like we were talking earlier. Instead of, you know, this guy, which is the same guy here, putting it through an input and having it come this way, this takes out this extra gate.
So am I allowed to do more than one camera?
Yeah, I mean, if you can.
Okay.
I mean, it's completely up to you for this purpose. It just doesn't say do it this many times. It doesn't say find this many different things that it has in common. It just says find something that connects them all.
Okay.
Does that make sense?
Yes.
So again, this could also not be the most simplified with respect to these 3 circuits. But it's more simplified than doing these 3 circuits apart. Yeah? Cool, so then from there we basically name these guys. The column's my favorite, A, B. Am I still on screen? Nope. A, B. And then these here where it's D and A. So these 3 would be our guys, and then these 3 from the second circuit, and these 2 from the first one. And then from here, you're basically connecting them all, seeing how they all connect. So to do that real quick, let me go ahead and write these guys out. You've got CA plus C prime D prime B. You've got C prime D prime B C plus CD plus B prime C prime, and then the third one is C D prime B prime. Oh nope, not B prime. AB plus AD. So this is basically what you're looking at now. So if we were just to look at this first one and start with that, you could start with any of these. So the CA are multiplied by each other, so we're going to use NAND-gate and have C and A coming in. And then the second one, a little bit bigger because we got 3 inputs. We got C prime D prime B. Alright, and then these guys add into each other. And then this is F1. So now we've got this guy already. And then we need these 2. So here we got C prime, D prime, and B prime, C prime, and then all of those going into OR gate here. We're just going to borrow that one. Can I see it now?
Yes.
Hmm?
Different function. Why is that from F1 to F2?
So, and this here,
Yeah.
this is our join term that we found up at join here.
Okay.
And so what we're doing is instead of creating this block again, we're just using it from the other function. It won't change anything to F1. F1's still just seeing that guy come into this OR gate. Does that make sense?
Like anytime if I have a different problem, like A and B, I can join them, or I have it has to be separate. If I have same situation.
The question is asking you to do that.
Already?
That's why we went through this up here, is basically we were looking for something that was in common on every single K-map to get something. So like I was saying earlier, it's not the most simplified, because on every single one of these we could simplify it more. But it's the same on all of these, and therefore we're taking out a logic gate out of this one and this one in order to achieve this. Does it make sense? And then we are doing the same thing for this last one down here. Is you're going AB, AD, and joining them into another one, which I'm going to make bigger. Not. And then this guy, we could go over this, and come in up here and get our F3. Everyone see that? Gonna make sense a little bit? Cool. Any other questions or anything that I could go over? It's kind of different mind thought than what you've been doing, right? You've been going from a K-map and just simplifying it, finding the simplest thing, because what you start with, Boolean algebra. How do I simplify this computationally, line by line, trying to make it as simple as possible? Well, here you're looking at using K-map to do the same thing. But now you're looking at, okay, I've got these 3 outputs I need with all these different possible inputs. How do I join them all together in order to make this circuit simpler? Now, if these 3 weren't joined together, then you'd have different logic here, different, possibly more logics. Maybe you could even simplify this down even more by looking at this and what's overlapping even more. I'm not too sure. Like maybe you could go in and mess with these a little bit. I don't know. But that gives you an idea at least what kind of problems 7 has to present. And this will be on our website in PDF form for you. Alright, and then hopefully we'll have these recordings up by Monday. Cool? Would you like to take a picture of it?